Now let us look at it. Let's we have already in the last lecture on shear we discussed what is the effect of pre-stress. So let us look at now what happens for a torsion. So this is a simple case how the shear stresses will develop when a beam is subjected to a torque like this. And now what happens to in fact torsion is a 3-dimensional shear stress distribution. In shear we have 2D, in torsion we have 3-dimensional shear stress distribution. Now, if you see how the principal stresses are going to develop, you can see here that now I am going to have crack like this. So, the crack, you know that crack is going to follow principal compressive stress direction, because the cracking will form perpendicular to tension. So, we have seen that, right. So, in this case it is going to be like this. So depending upon your nature of your stress distribution, I can convert it from Mohr circle, again we can convert it into principal stresses. Now, let us see how the crack pattern is going to be. You see here in a torsion, the direction of your principal stresses in all the 4 sides of the beam are going to change. So, you see here you get this kind of a crack like this on the front elevation side, on the top side there is a change in crack angle, and then on the back side you go like this. So, you tend to get this kind of a spiraling crack, because the principal stress directions will keep changing, and because of that the crack is also going to keep spiraling. Okay. This is the crack pattern that you typically have it in when you have a beam that is subjected to pure torsional moment. Now, what are the crack patterns? Let us compare how the crack patterns are going to be between a pre-stressed concrete beam and a normal reinforced concrete beam. And we know that the principle, by applying pre-stress, we are going to increase we are going to adding more compression. So, basically it will take more load before it can crack. So, that is a fundamental essence of pre-stress, because concrete is being weak in tension, we apply compression so that we can delay the crack. So, same philosophy also applies here for torsion as well, and you see here again this kind of a spiraling crack is going to develop in case of a pre-stressed concrete beam, and in RC beam this is the kind of crack distribution. So, typically we end up whenever we go for pre-stress, because we use high strength material, the amount of reinforcement that what we are going to put is going to be less, right, because the pre-stress is going to help me in reducing the shear demand, like what we discussed in the previous class. So, the amount of net reinforcement that what I am going to have in a pre-stress system is going to be comparatively less than the RCC beam. So, because of that you tend to have fewer cracks than compared to RCC beam. That is what we have seen in shear chapter as well. The shear also you see in pre-stressed concrete beam tend to have, in flexure also we have seen pre-stressed concrete beams tend to have lower cracks compared to that of RCC beam, because we end up providing less reinforcement, right. So, that is one difference. Now, what is the effect of pre-stressing? So, let us see, I take a pre-stressed concrete beam and it is subjected to, let us say, a concentric cable profile like this, and it is at an eccentricity E. If you take the small element A, and then if you look at the stress distribution, we have seen that in shear as well. Torsion is actually, as I said, this is a 2D element, this is a 2D element. Torsion you have to look at it in 3D. Okay. So, instead of a square element, we look at a cube element and look at the stress distribution, but fundamental concept is the same. So, you are going to have axial normal stress from pre-stressing. In addition to that, you are also going to have shear stress that will be developed, that we have seen it in the last lecture as well. Now, when you convert them into principal stresses, you will find that you will have principal compression in this, and this angle, if you take theta, we found that this is going to be less than 45 degree. If this is less than 45 degree, this angle has to be more than 45 degree. So, we have seen that. So, pre-stressing is going to make the crack angle shallower with respect to the horizontal axis. So, that is horizontal axis, this is this. That is why this I am taking that as a theta, which is less than 45 degree, right. Now, again this can be again expressed like this. So, here what we are seeing is from this plane right, to this plane which is principal tension, that angle is more than 45 degrees. So, that is why we are going from here to here, and you know that so basically what we are saying is we are coming from this horizontal plane which is originally this, right. From here we are coming to this FT location where alpha is going to be more than 45 degrees. Why? So, in Mohr circle then 2 alpha will be greater than 90 degrees. So, that is what we are measuring from this location, and we are going all the way to here, which is this is your FT plane, right. So, if this is the case, then this is going to be this, let us say it is 2 theta is going to be less than 90 degree. Okay. So, this is the theta angle with respect to the horizontal, right. Anyway, so we have seen that. Now, this is the same effect is applicable for shear induced by torsion as well. So, in net essence what we are saying is the stresses induced by torque are resisted by closed stirrups and longitudinal reinforcements along the sides of the beam web, and the distribution of torque along the beam is usually same as that of the shear distribution, resulting in more closely spaced stirrups. So, that means just like we have shear force distribution, twisting moment distribution is also going to follow nearly the same variation, and pre-stressing is going to increase a torsional cracking load or torsional twisting moment load, we can say, and then the stresses induced by torque after post cracking will be resisted by a space stress. A space stress will be formed. So, internally you will have space stress will be formed. Concrete between cracks are going to act like strut in compression, okay, and then you have stirrups and longitudinal bar are going to be in tension. So, they form a space stress in arresting the in resisting the applied torque. Okay. Now, let us look at what is the effect of pre-stressing between an RCC beam and a pre-stressed concrete beam. The red color curve what you see here is for the RCC beam, that means without any pre-stress. You see that it is cracking at a lower T cracking for RC, and see this is your T cracking for pre-stressed concrete beam. So, as expected, the presence of pre-stressing in or the presence of compressive normal stress is going to increase the torque at which it is going to crack. And then you see, but if I compare similar beams, okay, with similar reinforcement, there is no change in ultimate strength. Okay. But however, cracking torsion is increased because in fact, when from Mohr circle also we have seen that the moment you have axial compression, your circle shifts towards left and it is going to take more applied load for it to reach the principal tensile strength. That is the reason the cracking capacity increases, right. We have seen that. So, the cracking occurs at higher torque due to pre-stressing, and you can see here that it is evident from this blue color curve. You see here cracking torque is higher. Now, with further increase in the load, the crack pattern also remains more or less the same, but however, the inclinations of the cracks, how the crack angle is in each side or each plane is going to change depending upon how much pre-stressing it is seeing at that particular location, right. So, you can see that in net effect, pre-stressing helps me to increase the cracking torque, right. But once it cracks, the effect of pre-stressing is somewhat nullified, and I am going to have mostly it will be the other stirrups and longitudinal bar that is going to help in transferring the remaining applied torque. Okay, now let us look at now prior to cracking, how does these different cross sections behave. Now, this is a very good thin wall tube analogy. So, it is very easy for us to understand how different cross sections will resist the applied torque. Now, let us look at this is a continuous thin wall tube, and it is we are applying a torque like this along the longitudinal axis, a moment about the longitudinal axis. If I take the small element which is ABCD of a length dx, and then I look at it, and you will find that in each of this in the small element, each of the side, if you see, I am going to have a shear force VAB here, and in the plane CD I am going to have shear VCD, and so on. Now, the thickness of the tube is not constant. For example, if you look at this location, I am having a thickness of T1 here, and for example, if you look at this location, I am having T2. So, the thickness is not really constant, right. So, let us say that if I take the small element at B and I zoom it, at that location the thickness I can assume it to be constant, right. So, if you look at it, this tau, this is the kind of shear stress distribution that I am going to have at the location B, right. Now, we know that to satisfy the moment equilibrium, now you will find that tau 1 will be equal to tau 3 in terms of magnitude. The directions are different, and we know that. Similarly, here if you look at the element C, because at that element C I am looking at a small portion of this element ABCD at the location C. At that location we say that the thickness is not going to change much, so the thickness is going to remain constant. So, from this also, from your moment equilibrium, again tau 4 should be equal to tau 2, right. So, this is from this element and this is from this element. So, using that we can prove that shear flow, which is a product of shear stress and the thickness of the tube, will always remain constant. So, that is what we are trying to prove here. So, if you see here, if I take the horizontal force equilibrium for this element ABCD, if I take it, we can write that VAB is equal to VCD, right. So, the shear has to satisfy the horizontal force equilibrium, right. So, if you do that, then what is VAB? VAB is shear stress, let us say acting at the element is tau 1, and that is that having thickness T1. So, tau 1 into T1 into Tx. So, the shear stress multiplied by the thickness into length will give me the shear force. So, that is your VAB, and this is VCD. Similarly, at the location, if I look at this small element at C, then tau 2 into T into dx, because this is what we are looking at, right. So, this plane now we are looking. If I do that, the thickness is T2, so shear stress is tau 4 is equal to tau 2. So, that is the reason I am putting tau 2 here. Tau 2 into T2 into dx is same. So, dx. So, basically what we can say, dx will get cancelled, and you can write that tau 1 into T1 is equal to tau 2 into T2. So, that means this is there is a name for this, this is called as shear flow. Okay. So, that means the shear flow in a cross section is always going to remain constant. Okay. So, the tau 1, tau 2 are the shearing stresses acting on the sides A, B and C, D. So, the product tau T, which is equal to Q, is referred to as shear flow and is going to remain constant. Okay. So, this is the concept of a shear flow. Now, we will be using this for deriving some other expressions for cracking torque and twist per unit length and so on. So, that is the reason we should first understand what is shear flow and how do we know that it is constant. So, this is a simple element we are taking and applying the horizontal force equilibrium, and then applying from simple things that we can prove that the shear flow is going to be constant. Okay, now let us look at it. If I take this thin walled tube, now you see here, and now from simple thing, if I take the small elemental length ds, now at this point the resistance offered by the small elemental length is going to be q into ds. This will be the force, right. So, q is stress per unit length, right. So, that is what we said, tau is equal to, sorry, q is equal to Q is equal to tau into thickness that we saw, right. So, Q into ds length, that multiplied by R, if I am taking moment of this force Q ds about the center, then that will give me the resistance to the applied torque for a unit length ds, right. So, the applied torque will be resisted by Q into ds is the force multiplied by the distance if I am taking moment about the longitudinal axis. Now, the entire thing, if I am integrating over that perimeter, then I get my resistance to the applied torque T, right. So, now Q is going to be remaining constant through the entire length of this or the perimeter of this hollow tube. So, Q can be taken out. Now, I can just write this integration of R into ds as one thing. Now, what is R into ds? See, if you see here, R into ds is nothing but this one triangular area. And so, if you write, if I integrate for the entire length, we can find that. So, if I do that, basically what R into ds is this area, right. So, if I do that, in a way, what is that I am doing here is, if I define this area within the center line of the tube as this, right. So, this area is nothing but A naught, right. So, when I am multiplying R into ds, actually what we are doing, and we are integrating over the entire perimeter, you see that we are actually twice that triangle that we are taking, right. So, that is the rectangle area. So, that is the reason this becomes 2 into Q into A naught, where A naught is the area enclosed within the center line of the thin tube. Okay. So, now we got this. Now, what is the expression for shear stress as a function of applied torque? So, we can write that as T, Q is, we know that it is tau into T. So, tau, if I write that, so then we can say that shear stress is nothing but applied torque divided by 2 into A naught into T, right. So, for a thin walled tube theory, shear stress can be calculated from applied torque just directly by applied torque divided by 2 into area of this center line of this thin tube multiplied by the thickness of the tube. Now, we know that in torsion, it is the outer periphery that is actually subjected to more shear stress, right. So, for simplifying the calculations, I can convert a solid section also as a hollow section and quickly find out what are the shear stress and shear flow in the particular cross section. For example, this kind of a solid section, if let us say if that area is ACP and the perimeter is PCP, they can be converted into an equivalent hollow section like this. Now, what should be the thickness that I need to consider? So, that we have to find out. So, typically people have found that if you take thickness as 3/4 of ACP by PCP, then it is a good approximation as a hollow tube. Okay. So, there is I mean people have done some experiments and then there is no this is a good approximation. So, if I take thickness of that tube as 3/4 of ACP by PCP, then it closely predicts the experimental observation. So, that is the reason people have given this simplified formula. If I do that, my area A naught, which is the area enclosed by the shear flow, or in other words, this enclosed by the center line of this hollow tube, is going to be 2 into ACP by 3. So, if you do that, now cracking torque, like what we have said, it is going to be 2 into Q into A naught. Okay. From the previous expression that we have seen, we have derived this, which is cracking torque is nothing but 2 into Q into A naught. Now, how do I get my now cracking torque again in a say this thing? So, if I multiply this Q as tau into T, because Q is equal to tau into T again. So, tau into T. Now, what is the thickness? Thickness we have already taken that, you can assume this as a good approximation. So, you substitute all those things. So, finally, we can find cracking torque if I assume some tau CR, which is a shear strength okay, some shear strength concrete, okay. So shear strength of the concrete if I take, then I can plug in that value. So typically tau CR is some constant times square root of FCK. So if I assume that value, then if I can assume the thickness for the hollow section, then I can find out the cracking torsional capacity of even a solid section. Because again, even though you have a solid member, it is only the outer periphery will have more shear stress. So, we are assuming this as a hollow section and then trying to quickly calculate what is the cracking torsional moment. So, that is the idea. Okay. So, usually you see here cracking the shear strength is taken as 0.33 square root of F prime C, and F prime C here is a cylinder compressive strength. Okay. So, now let us move forward. Now, this is for without any pre-stress. Now, what is the effect of pre-stressing? Again, we have discussed that in the shear chapter, right. Again, torsion is a shear in the form of 3D. So, instead of taking a square element and we look at the more circle, now we are going to look at it in 3D. So, the same philosophy applies here. My pre-stressing is going to increase my cracking strength. Okay. So, somehow I am simplified way to include the effect of pre-stress. We are putting in terms of FCR, which is a modulus of rupture times square root of 1 plus FC by FCR as the strength that I need to consider the effect of, to include the effect of pre-stress, right. Now, tau CR is taken as 0.33 square root of F prime C. Now, TCR we have again we derived this formula previously. So, if you see here, if I put this formula for TCR, now TCR is tau CR into A square Cp by PCP. So, then again you see here tau CR I am putting here, right, and then I am just TCR is 0.33 square root of F prime C times A square Cpb by PCP times this is some kind of a amplification factor. So, if there is no pre-stress, you will find that cracking torque is only 0.33 square root of F prime C into A square Cp by Pcp, that is it. But if there is a pre-stress, just like what we have here, this is the formula that we are taking. So, it is just nothing but if higher the amount of pre-stress, higher will be your TCR. So, that is what we are trying to say. So, this is some kind of an amplification factor to include the effect of pre-stress, right. So, this is in this way any solid cross section can be converted into a hollow section and quickly we can find out what is the cracking torsional moment at which it will crack, right. And only thing what we have assumed is we have assumed some shear strength at which it will crack, right. So, always the shear strength and tensile strength is always square root of FCK or F prime C, depending upon what material property that you have. Okay. Now, how do you find the twist? So, we can invoke the principle of virtual work, external torque applied to create let us say a twist of theta. So, the work done is T into theta. Now, the internal work done is going to be, I have to integrate over the entire volume, shear stress multiplied by shear strain times the dV, which is an elemental volume. So, when you integrate that, so let us put now expressions for tau, gamma and see what we get out of it. Now, tau we know that it is equal to T by 2 into A naught T. Now, again you see here, so we can take in the volume element, let us say that it's same, it's subjected to pure torsion. So, let us say L can be taken out and we are doing integration only for the perimeter. Now, shear stress is T by 2 A naught into T and the dV is going to be thickness multiplied by the perimeter, over which that I am integrating, right. So, when you do that again gamma can be taken out and you can, and then you integrate over this T will get cancelled. So, it is gamma's shear strain on that particular cross section for pure torsion remains constant. So, that also can be taken out and I am integrating only the perimeter of the cross section. So, when we do that, you will find T into theta is nothing but applied torque length times shear strain divided by 2 A naught into P naught. Now, we are interested in finding what is the twist per unit length. So, the theta by L can be written as P naught into gamma by 2 A naught, which is basically this, which is typically denoted as psi. So, if you can find out shear strain, and the moment you assume your T, right, I can calculate my A naught and I can calculate my P naught. Okay, it is very easy, right. So, it is straightforward, right. Now, how do I find my shear strain? So, you can see that shear strain from simple, if you assume the system to be elastic, shear strain is shear stress divided by shear modulus. So, we substitute that. Now, I can find the twist per unit length as T. Now, this is what we got, theta by L. Now, gamma I am replacing that tau by G. So, this is what we have taken, right. So, this is your T by tau by G, which is nothing but your gamma. So, where tau is nothing but your, we have got that as T by 2 A naught into T. So, if you substitute that for any given torque T, if I know the thickness of the hollow tube and if I know the shear modulus, then I can calculate A naught and P naught, and I can substitute all the values and calculate what is the twist per unit length for an applied torque T. So, you see, we have quickly find out what is an expression for TCR, and we have found out what is the expression for twist per unit length.